So welcome back. In today's lecture, I am going to complete the infinite dimensional optimization problem. Okay, so basically here I am going to generate some kind of necessary condition, and obviously in last I will also talk about the sufficient condition. Okay, and what kind of difficulty basically comes into picture if we are going to talk about some kind of derivative that is called Gotex derivative. Goto, people are telling, or Gotex. If you see the name, then that looks like Gotex, but Goto, people are actually pronouncing that. So Goto derivative, then what kind of difficulty comes into picture whenever we are trying to convert the sufficient condition, sorry, necessary condition into sufficient condition. Okay, so we are going to examine that in today's lecture. So let us start that in order to talk about the infinite dimensional problem. So what we found that I have some kind of functional, okay, and functional we are going to talk about some kind of real valued functional, okay. So I have some kind of j, and here y is nothing but some kind of function, okay. So y is coming from some kind of vector space where element of vector space is nothing but functions, okay. And now whenever we are going to talk about the maxima or minima, I have to show that there exists some point y star, and y star, if you check carefully, so again that is function, okay, because whenever we are talking about functional, so y is function, and after that functional is nothing but function of function such that it will map to some kind of real number, okay. So this is called real valued functional, okay. It might possible I can able to define some kind of complex valued functional also, but we are not worrying. In this whole course I am going to talk about just real valued functional, okay. So I have to define the some kind of relation between or distance between y and y star. So I have to talk about distance between two functions, okay. So using Euclidean norm I can able to know the distance. If I have 2 points, then what is distance, but here problem is a little bit difficult. I have to talk about distance between two functions, okay. And due to that reason, what I have done, I have defined some new notion, that is notion of norm, okay, and that is generalization of absolute value only. So I have a space, and inside a space I have functions, okay. And after that, using help of that function, I can define the functions of function, that is functional, okay. And after that I am going to talk about the maxima and minima of that functional, okay. And function space, if you see the basis, so inside the basis I have infinite many element, and due to that reason, that is infinite dimensional space, we have already seen, okay. And due to that reason, this problem is class of infinite dimensional problem, okay. So now in order to check the distance between these two things, I can use any standard norm, okay. So in this course I am going to use C0 and C1 norm. I will tell you what is meaning of that. So let us start now the today's lecture. So let V be a vector space of functions, okay. So I am talking about this y star that is going to lie in this space V, and after that I have to check the distance between y and y star and their neighborhood. If y star is the extremum, means maximum or minima, and due to that reason, now I am going to talk about Banach space, okay. I am going to talk about some kind of a space where norm also comes into picture. So I have vector space. After that I have some notion to define the distance between two functions, so norm concept is required, and after that I have to converge to this point, okay. So I have to talk about convergence, okay, and convergent. But what happens that this point is not known to me, and due to that reason I have to talk about some kind of a space that is called Banach space, because inside Banach space, if any two convergent sequence I can take, any two sequence I will take, that is going to converge to the fixed point, okay. And due to that reason I am going to assume that whatever a space where I am going to solve the optimization problem, that is Banach space, okay. In previous class we have already seen about that, okay. Now What is meaning of local minima? That a function y star that belongs to a, okay, and a is nothing but that I have actually taken from the V, is a local minima of j over a if there exists epsilon such that y belongs to a, and if y minus y star distance between these two functions are less than epsilon. Okay, so in order to define the distance between two functions, you can take any standard norm. Okay, and after that, if this relation will satisfy for all point in neighborhood of y star, then I can tell that y star is local minima in this region, in local minima of this particular subset of vector space V. Okay, and if you see carefully what we have done in finite dimensional optimization problem, we are taking some kind of real valued function, okay, fx. Now I have just replaced x by y. So x here, x is coming from either some kind of column vector where each entry is real number, or some set x belongs to D and D is subset of Rn. Okay, and so due to that reason x and x star is nothing but some kind of column vector. So in order to move from finite to infinite, what I am going to do now, I am just going to change x. X is initially column vector where each entry is real number, to y. Y is nothing but some kind of function where each entry is functions, okay, real valued function. Now D here subset. Now I am just D, if you see carefully, then D is subset of this column vector, some kind of a space where each entry is form of column vector. I have selected that quantity. Now I am going to replace that by A, and A is nothing but that is going to contain some kind of functions. Okay, f I am going to replace by j. So f is initially function, now j is functions of function. Absolute value I am going to actually replace by some norm. Okay, and implicitly I am going to replace Rn by V. Okay, so if you see these two problems in this way, these two problems are very much correlated. Okay, but obviously I cannot tell that just studying the finite dimensional problem I can also able to solve the infinite dimensional problem. Let us check the difficulty, what kind of difficulty comes into picture. So I have told you that one of the key element whenever we are going to solve the optimality problem, I have to talk about distance. Okay, distance between two numbers. Numbers means here tuples of number I am talking about whenever we are talking about finite dimensional optimization problem. Now here I have to talk about distance between two functions. Okay, so I am going to consider two norms, that is called C0 norm, means some kind of function that is continuous, but I am not ensuring that each element is continuously differentiable. Okay, and after that another norm, generally we are using C1. Okay, and C0 and C1 in the previous class we have seen that how to define that. Okay, so maxima over x, that is in this interval a to b, yx I am going to consider. Okay, and L infinity, then I am assuming that since C1 assumption is there, so I can able to take the derivative, and after that I am going to add this. So in this way I have defined the distance between two functions whenever we are going to talk about the whenever we are going to talk about the 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 optimization problem of some kind of function or extremization problem. Okay, generally norm people are defining like that, but we are going to consider this. Suppose if something is two time differentiable, then I can add y double dash x between a to b. Okay, so generally people are taking these two norms. Now let us talk about the first variation and first order necessary condition, same like the finite dimensional. Okay, so how to do? Again I have to follow the exactly the same path. Okay, so what basically we are doing in case of finite dimensional case, if I have fx and x is some kind of element of the vector space where column vector, and after that what basically we are doing, we are defining x plus alpha, and alpha is some kind of a scalar, and after that we are adding some kind of y here. Y is coming from the vector space, column space, and in this way if I have unconstrained optimization, then I can move, okay, in the any direction. Here you try to see that I am going to do the same, that j is functional, that is mapped from V to R, and we have seen that whenever we are replacing this, after that just if I focusing on alpha, so with respect to alpha, variation of alpha, I have just a scalar kind of variation, and I can able to talk about Taylor series expansion. So similarly here I am going to do that. Okay, I have to define the derivative of functional here. At that time we are just talking about derivative of functions, and I know that how to talk the derivative of how to calculate the derivative of function during school time. But here now I have to talk about derivative of functional. Okay, so some extra element is involved now. So J map from V to R be a functional on function space. Now space is function because we are talking about functionals, that is function of function, and consider some function y. Okay, now whenever we are talking about the first variation, again what we have to do, we have to take some kind of increment. Again I am going to follow the same route. Alpha is some kind of real parameter, and after that eta I am going to take any element from V. Okay, now V, you can see if you check, then that is function, and due to that reason now I am going to talk about the addition, pointwise addition of two functions, that is just difference. And whenever I am going to talk about the first variation, now what I have to do, I have to substitute alpha tending towards 0, means alpha equal to 0, like that. Okay, so in the finite dimensional problem, here I am again taking alpha equal to 0. At that time we are talking about the derivative of this function. Okay, now here I have j, that is functional. So again similar way, what I am telling, that now I have some kind of linear function. What does it mean? That we know that if I have some kind of function, one dimensional function y, and this is fy or x, whatever you want you can write, and after that whenever I am talking about derivative, it means that here I am going to talk about some kind of tangent. Suppose if you are in two dimension, this is x and y, so now function is fx and y, so I have something, some ball kind of things I have, and whenever now if I have to talk about derivative, then we have to talk about some kind of transformation. Okay, linear transformation. Okay, and linear transformation will give us the physical interpretation of derivative in case of higher dimensional space. Okay, similarly here, since I am in some kind of a space where each and every element is function, so I have to search some kind of niche linear functional. That linear functional is going to approximate some point, and point is functions, with best possible accuracy. That is the interpretation. Okay, I hope that you are able to understand the interpretation of derivative in case of one dimension and higher dimension. In case of one dimension, that is nothing but tangent from tangent which is going to touch at this point. In case of higher dimension, I have some kind of best linear approximation that is going to touch here. Okay, so similarly in case of the functional, whenever I am going to talk about the functional and I have to calculate the derivative, then I am going to select the best linear possible linear functional which is going to approximate at this point, or best fit at this point, you can tell. Okay, so variation again I am going to define in same way, jy, and in place of now here we have seen that in case of the finite dimensional, this is Jacobian, so similar kind of things basically comes into picture here. Okay, and now this is the higher order term, and I am assuming that higher order term, if alpha tending towards 0, then that is going to vanish. Okay, and now I am going to talk about the I have told you that whenever I am going to talk about the infinite dimensional optimization problem, at that time I have to talk about the derivative of functional. Okay, so and this is nothing but the derivative or linear approximation, you can tell, linear functional or linear transformation. Okay, linear, whenever something is linear, it means that I am telling that alpha n1 and alpha n2, then this kind of relation will satisfy for all n1 n2, that is belongs to function space, and alpha 1 and alpha 2 belongs to R. That is the meaning. So linear function we are understood in this sense. Then now you can see that now I come to Goto derivative. So this is called Goto. So first variation as defined above correspond to so-called Goto derivative of J, which is just the usual derivative with respect to alpha. Okay, and here y and n I am assuming fixed. Okay, because just I have to vary this scalar. So in this way we are going to talk about the Goto derivative. So whenever we are talking about the first variation, so in case of the in case of if you remember the case of finite dimensional optimization problem, so at that time we are defining derivative like this, limit alpha tending towards 0, and this kind of things I am defining like j dash 0 like this. Okay, now in place of j dash I am going to define like this. Okay, now let us come to the first order necessary condition for optimality. So now what I am going to do, I am going to assume that y star is local minima of j. J is function of function, means functional, and some set A. I am just going to talk about the local. So I am going to just talk about the subset. So A is subset of V, and after that I am going to select the A is subset of basically V, and actually here Y that belongs to A. Okay, so just I am going to select the local minima in this region A. Okay, or minima in this region A. Okay, so now again what I have to do, I have to assume that Y star, this particular function is going to minimize this functional. Okay, so I have to check the neighborhood of y star, and due to that reason I have to define the neighborhood. Okay, and whenever I am going to define the neighborhood, that should be belongs to A, because I have to just check inside the A. So what I am going to assume, that I am going to parameterize with some kind of scalar alpha and eta that is going to belong to V, and alpha is very close to 0. We have already, because we have to take the first order variation, and again now what happens, that it follows that our definition of local minima and admissible perturbation this as a function of alpha as a local minima at alpha equal to 0. Okay, it means that we are telling that if alpha is tending towards 0, then j y star that maps to real number is minimum real number in all vicinity. Then I can talk about the minima. Similar way I can talk about the maxima also. Okay, so first I have to make sure that j y star should exist. Some case it might possible that that j y star will not exist. If that is not exist, then I cannot able to talk about this kind of condition. So I am assuming that that best possible linear approximation about the optimality point will exist. Okay, and after that I can able to write like this, and same like the finite dimensional optimality condition, whenever I am solving finite dimensional optimization problem, at that time what we have done, we have assumed that delta j means first variation that is not equal to 0. Okay, and we have given some kind of counter argument that if that is not 0, then what happens, I cannot able to tell that j y star is the minima. So similar way here if you proceed, because you can see that exactly in same way we are now actually approaching the problem. What I have done, again I have actually reduced the problem in terms of one scalar alpha. So same argument, okay, of finite dimensional optimization problem remains here, and due to that reason I have written here, applying the same reasoning that we used in derive the necessary condition for finite dimensional case. Quickly we can able to derive, quickly we are arrive at the first order necessary condition for optimality. And how basically we have proceed at that time, we are assuming this is not equal to 0, and if this is not equal to 0, then what happens, that negative case I have taken here, and negative case when I have taken here, then it is possible to show that if this is not equal to 0, then this y plus alpha n may be greater than jy. Okay, so and at that time minima will fail. So similar way we have proceed. Okay, now one more important thing is that you can see here that I have written Frechet derivative. Okay, so Gotex derivative, whenever I have talked about Goto derivative, so at that time Goto derivative, what we are assuming that for fixed y and n, I have defined derivative of functional same like the classical derivative. Okay, here what we have done, we have actually little bit different way I am going to define the derivative, and you are able to understand the reason why we are defining this whenever I am going to talk about the sufficient condition. For necessary condition, this is not so important, but in order to formulate the sufficient condition, this derivative, that is Frechet derivative, is required. And what Frechet derivative is telling, that y plus alpha n, that now I can define like this. Okay, so instead of this, now you can see I have this kind of definition. So here and now I am not going to consider the alpha, I am going to consider about the general eta. Okay, so eta that belongs to A, for all eta belongs to A, now this kind of approximation is valid. Okay, so difference is that now whenever I am going to talk about the Gotex derivative, so classical way I have defined, so same way I am just concentrating on alpha, but here you can see that there is no alpha. Okay, so now I am going to talk about y, and perturbation of y is eta, eta belongs to A, and in that term I have defined. If we are going to do that, then I am going to tell that this is called Frechet derivative. Okay, and it is possible to show now with help of Frechet derivative the difference. So it's just look like the difference of the notion, but that is not the case. Okay, it is possible to show that both derivative are totally different. Why both are totally different? There, in that case, we are just varying alpha, and eta is fixed. But in this case, I am varying eta for all A. Okay, so due to that reason, means this required a stronger differentiability condition than Gotex derivative. Okay, so it is possible to show that when Frechet derivative exists, then Goto derivative will already exist. Okay, so this is a stronger condition than the Goto derivative, and we are going to use this kind of condition when we are getting problem with the Goto derivative. Okay, now second order optimality condition, second order necessary condition. So first order necessary condition we have formulated just by taking first order variation. Okay, what is meaning of first order variation? We have just considered the first order approximation, and after that we are assuming that all term, higher order term, as alpha tending towards 0, that is tending towards 0. Okay, whenever we are talking about second order variation, it means that I am going to talk about the one more order of term, and same like the finite dimensional optimization problem, now we have to consider this quadratic term also. Okay, quadratic term means now we are going to talk about bilinear thing here. Okay, so linear, whenever something is linear, this is linear, at that time we are just talking about one argument. Bilinear means we are going to talk about two arguments. So we are telling that this is linear and this is bilinear. Okay, and and this is exactly correspond to the second order expansion in case of finite dimensional. So G0 I have already told you that same like G0. So G alpha, G0, G dash alpha, G. So in place of this, I have just replaced this. Okay, and G alpha, in place of G alpha, I have J Y alpha n, and in place of this, you can write like this. So just correspond to the finite dimensional optimization problem. Okay, those who has not attended finite dimensional optimization necessary and means necessary and sufficient condition, first order variation, second order variation, please again check the lecture. Okay, and again now with help of this I can able to formulate the necessary condition, second order necessary condition, and we know same like again proof is again the same, that we are going to assume that this is greater than 0, otherwise you can assume that this is less than 0, and less than 0, and you can create some kind of contradiction. So you can assume that this is less than 0, and by proof by contradiction, what you can do, you can prove that delta j y star eta that is greater than equal to 0. Okay, so whenever we are talking about the second order optimality, second order variation, at that time we are assuming that whatever higher order term, here basically one thing is missing like this O alpha square. So we are assuming that by alpha and limit alpha tending towards 0, that should be 0. This kind of assumption I have, alpha square. So now what is second order optimality condition? If this is positive semi definite, then I can tell that this is second order necessary condition. Okay, so first order necessary condition and second order necessary condition is exactly same like the finite dimensional optimization problem. Okay, so finite dimensional case, I am just define the classical derivative, and after that quadratic function, and after that whatever matrix that comes into picture, Jacobian matrix comes into picture, we have shown that should be greater than 0. Okay, here everything is just converted into functional. Okay, so please be careful that here y star is function. Okay, so now what happens, whatever matrix that is going to comes into picture where function are involved. Okay, and at that time we have to check that is positive semi definite. Okay, so again similar like matrix theory we are going to use here. Okay, now let us come to the sufficient condition. Okay, so what we have observed from finite dimensional problem, so when we have solved the finite dimensional optimality condition for local minima, at that time what we have done, we have taken first order variation, and using first order variation we have generated the necessary condition. After that we have taken second order variation and we have generated the necessary condition, and after that what we found that if this condition, this second order necessary condition, if we remove the semi definiteness from here, means if I convert positive semi definite into positive definite, and if I consistent with respect to first condition, first means first order necessary condition, and what is first order necessary condition, that delta j y star that equal to 0. Okay, so I have written here same. So combining the first order necessary condition with the strict inequality counterpart of second order necessary condition, I can able to show that this happens. Okay, same like this is exactly the same like the finite dimensional finite dimensional, whenever I am talking about finite dimensional local minima. Okay, or and strict minima, sorry, whenever we are talking about the sufficient condition, at that time we are going to talk about a strict minimum. Okay, but it is possible to show that here y star is not a strict local minima. Okay, so according to definition of local minima, we have to must show that j y star is the lowest value of j in some ball around y star. So that kind of things we have to show. Okay, so in case of the finite dimensional case, I have finite dimensional means x star. So in nearby of x star, I can create some kind of unit ball, and it is possible to show that unit ball and since whatever space I have considered, that space contain the column vector, so that is closed and bounded. Okay, so if I am able to give the guarantee that a space is closed and bounded, then I can able to talk about the strict minima. Okay, means whatever minima that comes into picture, that value is actually minimal. Okay, and due to that reason I can able to talk about strict minima in this space. Okay, but let us try to see that similar kind of formulation is possible for the infinite dimensional problem or not. Okay, so what we have done so far, we have tried to do generalization same like the finite dimensional case. So I preserve the first order necessary condition, and I have just changed the second order necessary condition to a strict condition same like finite dimensional case. Okay, and after that what we are telling that in finite dimensional case, if I have some kind of subset that is going to form some kind of compact set, closed and bounded set, then I can tell that x star for this function fx, and here our problem is Rn to R. Okay, so this x star is local minima for that compact ball or compact set. Okay, but let us try to see that difficulty in case of the infinite dimension. Okay, so the problem is that term O alpha square and hence epsilon depends on the choice of perturbation eta. Okay, in this case, now because I have to show that whatever minima that contain the lowest value, so in finite dimensional case we took the minimum of epsilon over all perturbation in unit length, but we cannot do here because the sphere in infinite dimensional V is not compact and Weierstrass theorem doesn't apply. Okay, so what happens that if I take the unit length of a sphere, and if I can vary the perturbation in this region, means epsilon I can take minima, so minimum value of epsilon will talk about the strict minima in case of finite dimension. But if you form same kind of ball in infinite dimensional space, it is possible to show that that is not compact. Okay, and due to that reason I cannot apply the Weierstrass theorem. Weierstrass theorem, what Weierstrass theorem is telling, that suppose if first order necessary condition remains the same, second order necessary condition is converted into a strict condition, and if I can able to select some kind of compact ball where all perturbation will lie, and if there is minimum, then we have a strict minimum. Okay, but difficulty in infinite dimensional case, if you select unit ball, it is possible to show. I am not going to show here, please check the literature everywhere, means that proof is very simple, that if you create some kind of ball in infinite dimensional space, then that is not compact. Okay, means that is not closed and bounded, and due to that reason, now in order to generate the sufficient conditions such that I can talk about the strict local minima, I have to again restate the second condition. Okay, and it is possible to show that if further I can assume that this delta second variation of functional, if that is greater than lambda is some kind of number, and norm of eta square, norm of perturbation square, then that will gives us the strict local minima. Okay, and from this condition, that second variation that is greater than equal to 0, this condition, it is possible to show. I cannot tell that delta j y star eta is greater than some kind of lambda or norm of this. This doesn't imply this always, and due to that reason, now what we have to do, we have to think something different. Okay, so now it is possible to show that if I replace the Gottov derivative with Frenchet derivative, then because using Frenchet derivative, I am not going to parameterize y by alpha, some scalar. Now I am going to talk about general perturbation eta, and for general perturbation eta, now it is possible to show that if you take the second order variation, then that is function of eta square. Okay, and from here I can able to generate now this kind of condition. Okay, so if I replace the Goto derivative with the Frenchet derivative, then it is possible to show that there exists a strict local minima. Okay, and due to that reason we have to also talk about the Goto derivative. Okay, so let us again try to see that first order necessary condition is exactly same like the finite dimensional optimization problem case or optimality case. Okay, so suppose that if I want to calculate the finite local minima in case of finite dimensional optimization problem, so just I have to make sure that first variation, okay, and whatever linear approximation I have taken or a linear transformation we have taken, that should be 0. In case of second variation, I have to show that that is greater than equal to 0. Okay, and that is second order necessary condition. So that is again exactly remains the same in case of infinite or finite both. But whenever we are going to talk about sufficient condition, then difficulty is that whenever we want to generalize it for a strict minima in some subset, difficulty is that if I create some kind of unit ball, then that is not compact. And due to that reason, I cannot able to talk about the sufficient condition, okay, or optimality using the Goto derivative. Okay, so we have to select another derivative that is called Frenchet derivative. Okay, and same kind of things actually I have written here, that using with our current definition the first and second order variation in terms this, we do not have a general second order sufficient condition for optimality. Okay, but if you replace these two, Goto derivative by Frenchet derivative, then obviously this kind of relation will satisfy. What finally we have to do, if I am able to show this kind of things, then I can able to find that there exists a strict minima. Okay, a strict local minima. Okay, and for that I need Frenchet derivative. Okay, so now let us conclude the today's story. What we have seen, that I have some kind of functional and I have to talk about the local minima of functional in some subset of the whole vector space. Okay, sometime it might possible I have to search in whole space. At that time we will tell that global minima. Okay, and for that we have generated this two necessary condition. Okay, and with help of necessary condition we trying to generate the sufficient condition such that I can able to talk about the strict local minima. Maxima is actually opposite of that. Okay, due to that reason we are not going to talk about maxima, because if we are able to solve the minimization problem, then opposite, just you can take the negative sign, then we are able to solve about the maximization problem. Okay, so how to resolve this derivative? So I have to talk about some general derivative. Okay, concept of general derivative, that is called Frenchet derivative. But in this course I am going to use Goto derivative, because it is possible to show that whatever way we have going to formulate the problem, we are using first order sufficient condition or second order first order necessary condition and second order necessary condition, we are able to achieve the strict minima. Okay, but that is generally that is not true. But in control course, if we are assuming that whatever optimal control problem I am going to consider, okay, and solution will exist, means piecewise continuous in T, locally Lipschitz in X, these kind of assumption we are going to assume, then just using two sufficient condition I can able to arrive to the strict local minima in case of the infinite dimensional problem too. Okay, so with this remark, now class is in from my side. So if you have any question, then please let me know. In next class onward, now what I am going to do, I am going to on the problem session. Okay, so fundamental is over now. Okay, so what we have seen in fundamental part, I have some kind of finite dimensional optimization problem. I have some kind of infinite dimensional optimization problem. So how to formulate the necessary and sufficient conditions such that I can able to talk about local minima and strict local minima. In order to talk about global minima, I have actually assumed convexity condition. Similar kind of things here also we have to do. Suppose that if you are going to talk about the global maxima or minima, then I have to take the help of sufficient condition. So I have to take the help of Goto derivative, means Frenchet derivative. Then I'll end up to the local strict minima. And after that, if I assume that region is convex, then that local strict minima is also global minima, like that. Okay. So this 5 lecture we have just talked about the basic of the optimization problem. Okay, now in next class I am going to talk about, suppose that if I have infinite, obviously in this course I am just talking about the infinite dimensional optimization problem. Okay, finite dimensional optimization problem I am not going to solve in this course, but we are able to get very good feedback from the finite dimensional problem, that how basically finite dimensional problem is different from infinite dimensional problem. Because what we have seen, that first people has developed some kind of finite dimensional problem, and after that they land up to infinite dimensional problem. So we are able to see the root, how basically infinite dimensional problem comes into picture. And now what we are going to do, we are going to involve the constraint. And again, what we found in case of finite dimensional optimization problem, if constraint comes into picture, then we have defined the Lagrangian, and after that again we have transform unconstrained problem to constraint problem, and after that we have solved it as usual way. Similar kind of things we are going to do in next class. Okay, so now class is in from my side. If you have any question, then please let me know.